Welcome, everyone. My name is Chris, and I'm the project manager for Cascade Consultants. We are very happy to present you with the design of our City of Valparaiso Public Works Facility and Utilities Campus. Before I jump into some of the actual design work that we've done this semester, I'd like to introduce the team that made everything happen. So like I said, my name is Chris. I'm the project manager and the lead environmental engineer on the project for Cascade Consultants. Next, we have Nick Halen, and he is our water resources engineer. Geotechnical side of things have been headed up by Raul Gupta. Eric Swope is our structural engineer. Danny Antunes is also our structural engineer. And finally, Michelle has been looking into the transportation side. So what are we doing? What are we as a company doing to help Valparaiso? We are trying to produce a satisfactory product in the form of a public works facility and utilities campus. Within this project, it kind of summates to 4 big buildings, which the structural design team will be talking about. And those pertain to the vehicle mechanic shop, an office building, a salt structure, and a fuel station. Next, the site has been used as a dump, so there's a lot of environmental work that has to be done. But overall, we're trying to produce a satisfactory product that will help not only the employees that will be working at this facility, but also to help empower the citizens as a whole of the Valparaiso community. So a little bit of background just to get you guys caught up. First off, the site is located just southwest of downtown Valparaiso. As you can see here, this is what our parcel of land looks like. You all have handouts, and that's the final design of the site, and that's when everything is on there. So you'll be able to kind of follow along and see how everything gets designed. Next, we have the site. It is approximately 80 acres in size. What makes this site kind of interesting is that you'll see on your handout that there is a large area down here. Those are wetlands, and that is an area that we need to protect and we cannot harm. Any impacts that happen to that area is very detrimental, and we really need to make sure that those are limited. And finally, the site, as I have said, has been used as a dump. So as you can see in the back here, this is all mounds of road spoil and street sweeping, and that brings quite a bit of contamination onto our site. So this is just an overview. This is exactly what you have on your papers, and it's just kind of to help you out so you can see everything that we've done as a team to make this project successful. So why do you need me? Why do you need an environmental engineer for this project? The reason is because of these street sweepings and road spoil, as I've said. This site has been used as a dump for 30 years, causing different contaminants such as VOCs or volatile organic compounds. What that means is those are compounds or elements that are very unsteady, and if you heat them up, they will produce vapors. These vapors can be very toxic to human health, and we cannot have those on site. So it's my job to make sure that those are not harming anyone on the site. Next, arsenic, which is a heavy metal. Heavy metals are very detrimental to health as well, so we're going to take care of that. And finally, just general pollutants from different automobiles and cars. So as I said, road spoil and street sweepings generally come from a road, and roads are used primarily by cars and trucks. And all of the things that could come off of a car and be harmful to human health often get taken into the road and have been transported to our site. So what have I done? I have helped design 4 key design elements. That is a capping mechanism, a thermal treatment of the soil, a vapor intrusion system, and a passive wall. And now we're going to jump into exactly what each of those are. So first of all, on our site, you'll see near Joliet Road, there is a large depression there. This depression area is kind of outlined by this trapezoidal shape. What I have decided to do with all of the dump and waste material located on site is move it to that depression, which is seen here by this white space. So we're going to put it right here, and then we're going to cap it with a clay-like material. And that clay is capping it in order to ensure that no contaminants leach out into the site and become harmful to human health. And then on top of that, it's going to be very productive because we're going to put a road right on top here. So that's going to bring the site up to an elevation of about 703 feet, and it's going to make for a perfect elevation for the road, so it's nice and smooth transition into our site. Next is thermal desorption. That is just a really fancy word for using heat. So we're going to be using heat to treat all the soil under our buildings. The reason we do that is because, like I had said, by introducing heat into the system, these volatile organic compounds become vapors. As these vapors become more and more concentrated, they become harmful to human health. So what we do is we bring it into a system that looks similar to this. We load it with a loader, something that looks like this, and you put it into this system. And as you can see, all this steam, the the system actually takes all of the vapors that come out of the soils and treat it. So this way it's no longer harmful to human health, and we now have usable soil for the site. Next, I designed a vapor intrusion system. This is just a fancy word for saying protecting the buildings. So what this is doing is we're going to implement a system to make sure that all of these vapors that come through the soil do not get into our buildings. So this system utilizes a series of pipes and fans to suck the contaminants out from under the system, from under the buildings, and get them away from any type of human health. The only two buildings that we're going to be doing this under will be the mechanic shop and the office storage facility, excuse me. And the reason we have decided to just do it at those two buildings is because we want to make sure that all human health is safe. And those are the two buildings that will primarily be having humans working in there. The final thing that I have been working on is a passive wall. So basically what this is just, if you look on the southern portion of your site, you'll see a wetland. That wetland needs to be protected, and this is going to do exactly that. This type of wall is going to be about 800 feet long, 36 feet deep, and 4 feet wide, and it's going to be backfilled with a bunch of stone. This stone allows for a very effective way for any type of vapors that will move through the wall to come out of the site, and if that happens, that way the water that goes through it will no longer be able to make it to the wetlands contaminated, and that's the general goal, and this also makes all of the agencies happy, like the EPA and different agencies like that. So just to kind of help you guys out, this is where the capping mechanism will be that we talked about. Under the office building and the garage is where a vapor intrusion system will be implemented. The passive wall will be right along here to protect the wetlands, and then the thermal treatment of the soil will happen anywhere that a soil is excavated underneath a building. So when it's all said and done, my environmental engineering aspect of this design will cost just about $1.9 million. And with that, I'm going to pass it on to Nick so he can talk about the water resources aspect of this project.
Well, thank you very much, Chris. And as you said, my name is Nicholas Halen. I'm the water resources engineer for this project. And today we're going to be kind of going over exactly what I did throughout this year and what a water resources engineer is all about. So with water resources, what I'm kind of concerned about is all the rainwater that we're receiving on the site and where is that all going to be going, as well as all the water that's going to be coming into the site for water for be using in all the kitchens and bathrooms in the buildings, as well as the water going out of the site called effluent, which is more of like your sanitary and also your storm sewer. And going through this all with the main four key design elements I have here, the stormwater treatment, water distribution system, storm sewer system, and the sanitary sewer system. And now we're going to go into a little bit about each. So first with the stormwater treatment. So pretty much what we want to do is making sure we can get water to, it's called infiltrate into the soil. So actually soak into the soil as much as we possibly can. So that way less water then is exiting out the site and then introduced into our storm sewer system. And through that design, I cut up with called 3 different best management practices. The first being rain gardens. So you see these around Walmarts and big retail stores. Not only do they allow for the water to infiltrate into the soil, but also adds an aesthetically pleasing element to the design site. And these are actually placed throughout the design of the whole entire project site. You can see placed around the buildings, and they all vary in size, but they all have the same kind of structure with the amount of soil types that they're using underneath them in order to optimize water getting into the soil. Next, we have the bioswale. So the bioswale you can see on your diagram is located on the southern portion of our site. So that is going to be allowing basically for another way for water to infiltrate into the soil, as well as water to then flow through the site and onto our west side where we have a catch basin which is elevated up so that way mulch and other plant material like doesn't get into the catch basin. So catch basins you can see right on your like residential neighborhoods, so the little metal grates that are on the street. This allows water to get into the storm sewer system and then out to the collection place. So with that, with the bioswale, here's a cross section that we have. So the water is going to be flowing through this way, and then these are all the different layers that are through on the underneath, and then the plants that we're going to be planting here that just allowing to slow down that flow. That way, it's not just all impacting the system too quickly. Next, we have filter strips. One of the unique elements about this site is Crystal Site, and we have this wetlands and kind of like this forest area that's around there. So we just need to make sure we can rehab this area. It allows for more water to then get into our soil and making sure that we can then slow down flows even further. Next, we have the water distribution system. So this is all the main pipes that are going into your house, like I said, for bathrooms and other sinks and such. So one of the main things that controlled my design was actually designing for fire flows. So if a fire were to occur on the site, making sure that we have enough water so when the firefighters come to the site, they can then hook into all the fire hydrants and be able to properly extinguish the fire. and that is what controlled all the different sizing and elements and links. Next, the two elements here, we have the storm sewer system and the sanitary sewer system. So these are based on kind of like the same design principle. They allow for gravity to then take the water based on the slope and then get it out to our west side of our site. That way we can tie onto our existing connection, one for the sanitary and storm sewer system at Joliet Road, and then for the water distribution system, since that's a pressurized system, getting off of West Side Park, a little residential neighborhood over there. And so here's kind of the underground pipe network that you see here. So as I was describing, so we have Joliet Road coming up here where the pipes are going to tie in with the existing connection, and then the West Side Park that we're having the pipe connect in for the all the water that you're going to be getting in your buildings. So with all said and done, adding up all the different elements of this project, the total cost for all the different elements that I designed is $1.2 million. And with that all said and done, I'm going to invite up Raul, who's going to be talking about the geotechnical scope of this project.
Thank you, Nick. I'm the geotechnical engineer for this project, and these are the design key elements I was looking throughout the year for this project. These are foundations, settlements, and the pavements. Now going in detail for each of them. Foundation. As you know, there are 4 structures on the site, as you can see in the handout as well: office building, mechanic shop and the vehicle storage, fueling station, and the salt burn. So I need to design the foundation for all of them. So there are the different alternatives that was chosen for the foundation. They were deep and the shallow. Deep. For the deep, we are doing the pile for the mechanic shop and the strip footing for the office structure. This is the process I was following throughout the year for the geotechnical part. This is designing the soil profile from the boring logs that we got from the owner, calculating the getting the column loads from the structure engineer, evaluating the bearing pressure of the soil, settlement calculation, different types of footing for that, loads and designing them, and reinforcement, and finally the cost estimation. This is a boring soil profile we designed from the boring logs we got from the owner. As you can see, the mechanic shop and the vehicle storage lies somewhere around B3 to B6, and the office structure lies somewhere around B1 and B2. And this is the layer of this soil that lies below the foundation, below the ground. This is all 11 feet of clay. So we can't rely on the clay for the loads we are getting from the structure. That's why we are using a driven piles for that case. But over here, the office structure, we have a sand and a gravel. So we can rely on that for the loads we are getting for that structure. This is the design of the pile we are using. As I said, that there's 11 feet of clay for that. So we are going 13 feet deep for that, and so that we can rely on 2 feet of sand and the friction we are getting from the pile. This is a timber pile we are using, and one pile can hold up to a load of 45 tons, and the maximum load we are getting from the mechanic shop is 90 tons, so we are using a combination of 2 piles. This is a layout of the piles. As I was saying, the loads we are getting from somewhere around here is 90 tons, so that's why using combination of 2 piles. But over here, over at the edge, the loads is somewhere around 20 tons, so we are using a combination of 1 pile. This is a strip footing we are using for the office structure. As the soil below the office structure is not the clay, so we are using the shallow foundation for that, and the loads we are getting for that structure are just the wall loads, so that's why we are not using the spread footing for that case. We are using the strip footing for that case. And finally, the cost estimation for all of that: the pile cost somewhere around $110,000, shallow foundation cost $115,000, and total summing up to $260,000 for the geotechnical part. Now I'd like to hand over to Eric to talk about the structural aspects of this project.
Thank you, Raul. Over the past 9 months, the structural team at Cascade Consultants has designed a mechanic shop and vehicle storage building, a salt storage facility, an office building, and also a fuel station. So turning onto this slide is one of the buildings I designed for this project, which is the mechanic shop and vehicle storage building. Some key features of this project, or of this building, excuse me, is the building will be roughly 540 feet long, which consists of 19 bays that are 30 feet wide. In the center of the building, on your handout, is lateral bracing, which will be used for a storage area in the building. And also on your handout, you could see that there's a road at the northwest corner of the building. The northwest corner of the building will be used for the mechanic shop, and so vehicles will be allowed to traverse completely through the building with garage doors on both sides. And then on the south end of the building, there'll be garage doors along all the bays with the exception of the interior core here. which is the laydown area for equipment and various pieces of equipment that they need to store in the building. The lateral system is used to resist the wind loads that will be the building will take, which will be resisted along here, 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 and here. And also, if the wind was to come from the east and west direction, it will be resisted by these four cross bracings positioned there. Another thing to mention is there will be Z-girts, which are basically, it's a fancy word for a beam that's in the shape of a Z, and it'll transfer the load from the outside of the building, which will be insulated metal panels, along the Z-girts to the columns and eventually down into the foundation. This is a side view of our building. Right here are the lateral bracing, which will be 1 1/4 inch diameter steel rods, which will be connected to the columns here and down here, and then the Z-girts along the side. This is the north end of the building where the 2 garage doors will pass through. It will be roughly 16 feet high to allow tall vehicles such as dump trucks to pass through if they're getting their oil changed. Finally is the cost, the money side of the project. We're sitting at just over $3.4 million, which is roughly $63 per square foot. We did include some contingencies along the way to account for some flexibility if the client wants to change the style of the building or if they want to make the building a little bit larger. So passing on to the fuel station, it's a very simple structure. I just have 2 columns with some cantilevered beams sticking out over the side here. We will be using HSS members to minimize cost, which HSS member is just basically a hollow structural steel member, which uses less material, which lowers the cost. With that, this is a breakdown of the cost. One thing to note is we're using an above ground storage tank instead of below ground because we have contaminated soil, and it also minimizes the cost for excavation. With that, I'll pass it on to Danny Antunes to talk a little bit more about the salt storage facility and the office building.
Thank you, Eric. Hi, Mom. So moving right along, as you mentioned, my name is Danny, and I conducted design on the salt storage facility and the office building. I actually have a couple examples here. Down here, we have 2 more simple kinds of structures. So this would be your office building and your salt storage facility. And then up here, I have a more modernized office building. And if you've ever gone down the road and wondered what these things were, like, well, this went off, but top right, that's actually a salt storage facility, but it can also hold other materials as well. So one of the elements, main elements that I designed in the office building was the truss. So if you can see here, here's my diagram of my actual truss. So my truss will be spaced 5 feet apart and will be connected with wooden members that are 4x8s, and also the members inside those trusses will be 4x8s as well. And they will be connected by metal plates and bolted, which will keep the whole structure intact, and you will have your whole truss if you look at that diagram that way. So the walls of my office building will be concrete blocks that will be reinforced. So I will just be sticking rebar in between the block holes, and that will hold the wall together, and it will hold the wind loads that will hit the side of the walls. Here's a little breakdown of once the actual wall is built, the other elements that will go into it, such as like brick veneer, insulation, your gypsum board, and all those other kinds of things. So obviously we're going to have windows and doors, and you want to have the proper support above those areas. So what I'm going to do is I'm going to add something we call angles. So they're basically just L-shaped steel pieces that are going to span a little bit where the opening is, outside of the openings. And it's going to hold up the bricks, instead of just allowing them just to fall through, so we can prevent a catastrophe just like that. So the total building cost for my office building will be $644,000, and this is essentially what it would look like. So for my salt storage facility, I chose to design the frames of that building using HSS members, which are essentially hollow pipes, if you look here, and they are square members. And here's a little diagram of how I'm going to weld those pieces to plates that are going to be bolted together and are going to hold the structure together. The framing of the entire facility will also be placed on top of concrete columns that are going to hold it in place so it doesn't just tip over. And this is essentially what those would look like as well. But mine will be all the way to ground level, so you don't really need to see them. And there's really nothing much to do but just bear all the weight. And here's a little diagram as well of how that's going to be conducted. I'm just going to bolt steel plate on top of those concrete columns and then weld the HSS members to that plate. So the total building cost will come to around $350,000, and this is pretty much what it will actually look like. So, and I will pass it on to Michelle to talk about the transportation portion.
Thank you. So as the transportation engineer, I had three main things that I had to design: a safe and efficient entrance, an adequate parking lot, and paved surfaces throughout the campus. So my first task was to design the pavement. There are three locations that I based my calculations off of. The parking lot isn't going to have that much weight on it because it's just going to be standard vehicles using this area. So the asphalt is only going to be 2.5 inches, and a base layer will be 5 inches. For the paved surfaces and auxiliary lane, those will be holding a little bit more weight. So the asphalt will be 5 inches, and it'll have a 6.5 base layer. Now the entrance, as Chris was talking, we're gonna cap it, and that means that there's gonna be clay underneath it, so we need a little bit more strength. So we'll have 5 inches of asphalt and 12 inches of base layer. So this is an overview of what the campus is gonna look like, and you can see the road and the different changes and the parking lots. So first is this transition right here where the road is gonna change direction. In order to do that, I had to do a horizontal alignment, which is basically what you're going to see from above. So I had to calculate the radius here, which would be 353 feet, and that allows for vehicles to move and change direction without having any problems. Next is this area right here, this is a slight S. It's very small, so you can't tell as much, but that is 2 quick changes of direction. So this first part right here is similar to the one above, and it also has a radius of 353 feet. And the second portion right below it right here has a slightly bigger radius of 354, and that is just so that the roads meet and it's a smooth transition between both of those turns. This is the vertical alignment, which this is a side view. As you can see here, there's various changes of elevation. So this is what the road looks like from above, but if you were to drive on it, you would experience all these changes of elevation. So this is the entrance area where we had the depression, and this area right here contains most of the road spoil and street sweepings. So we will use this right here and fill this area. And this also depression area is also pretty wide, so we will use the rest of the soil that's here and here to make this a flat elevation of 705 feet. Therefore, there won't be very much vertical change from the road. And next, I will discuss about this auxiliary lane to the north of the campus. Currently, right now, it's just 2 lanes, and there is a railroad crossing really close to the entrance of the campus. Therefore, after a train passes, there is a buildup of cars as somebody is possibly waiting here to enter into the campus. So what I decided to do was add an auxiliary lane, which is basically just this additional area here that allows for cars to pass by the car that is waiting to turn left into the campus. And this minimizes accidents that may happen in this area. And finally, the parking lot located around the office building. So the parking lot was based off of standards from the city. It is based off of the square footage of the building that the parking lot is for. So in total, these are 90 spots. So it's sufficient enough for all the employees to park. There are 75 employee vehicles that will be here. And it also allows for guests to have parking spaces. I also added 4 disabled parking spots, and 2 of those are van accessible. And the material is what provided most of the costs. So asphalt, we're going to use 2,200 tons. For the base layer, we're going to use 3,600 tons. There will be 3 signs added at the entrance, which will help drivers through the auxiliary lane, and there's also going to be striping added so that you can differentiate between the road and the additional area. And the total cost for transportation will be around $431,000. And I will give it over to Chris.
Thank you, Michelle. All right, so the moment you've all been waiting for, the overall project cost. So when it's all said and done, we're going to look at a final project cost of just over $8.2 million. And that includes all the different kind of sections that we've gone over in this project. So with that, I would like to thank you all for coming out to listen to our spiel about a project we've worked on for an entire year. And I would like to invite my team back up and allow you guys to ask some questions. Yes.
Can you tell me why you decided to place the facilities where you did and how that had an impact on the overall project?
Sure. So the way the site was positioned, it was very long. Oh, thank you. It was very long and narrow. So at its widest point, it was roughly 370 feet wide. So based on the way that the site was laid out with the wetland to the south and an active railway to the north, we wanted to shape the buildings lengthwise to maximize our space. Another consideration we had was the soil conditions and the contamination. So based on our soil borings that Raul utilized to design the foundation system, we wanted to try to maximize the size of the building, but also try to minimize the cost for foundation work. So the soil is a lot stronger towards the west side of the parcel, so we wanted to put the office building and all the parking spaces over there. And the mechanic shop, since it's such a large building, it's going to store roughly 30 full-size triaxle trucks and possibly more vehicles if they push them together. So we wanted to make sure we had the room to fit the building, but it was basically laid out based on the restrictions from the wetlands and the railway, and we only could really span east to west. But we try to position as close as we could to the west without intruding on the railway and adjacent parcels of land. Does that answer your question? Thanks.